So let's just start out. There are some in particular that I want to make sure I cover. And then we're going to pick some that y'all might have a problem with, okay? All right, we got started with number 3, didn't we? Yeah, we did the first part of that, and I overread the second part of that question on part B, where it said do the instantaneous. Well, you know, anytime you hear that, it means take the derivative, and that's all you had to do, okay, is take the derivative on that instantaneous. All right, what about number 1? Did everybody do number 1 okay? Okay. Yeah, 1.4 I and negative 1.3 j, and then take arctan to find the direction, okay? And then to find the magnitude, you do what? Square root of the squares, right? Now, okay, so what are we going to call this? We're going to call this we're just going to call this chapter 3 problems. I guess it is part 4, because it's like the 4th or 5th video, okay? And we're going to also call this review, okay? All right, so do we need to look at number 1, or do you want me to move on to another one? Move on, okay. What about, did everybody get the fireman problem? Number 20. Is everybody pretty successful with that one? Number 7. Okay, let's look at it. Yeah, because that's that might be a hint, might be a good test question, okay? Could. All right, so let's look at number 7. All right. Okay. It's a little bit lengthy. Now, I'm not going to, on these test problems, I'm not going to give you 3 or 4 parts to every question, every problem. You know, I may give you a few that'll have 2 parts, but most of them will be one answer. But then again, there will be a few that you'll have to do 2 answers, okay? All right, but I'm not going to give you 4 or 5 parts because you'd be there all day. All right, so number 7. So let's look at number 7. All right. We got the coordinates of a bird flying in the XY plane. Okay, so we got a bird flying. Okay, so let's draw our bird. There's his beak, and here's his wings. Okay, he's flying. All right. And let's go ahead and draw. It says in the XY plane, so go ahead and draw your X and your Y. Okay. And it is flying in the XY plane are given by this, and it says that X with respect to T is equal to what? Alpha times time, is that right? Alpha T. And that Y with respect to time is equal to 3 meters minus beta T squared, right? Okay. All right. And then it tells us what alpha is. It says that alpha is what? 2.4 meters per second. Okay. And that beta is 1.2 meters per second squared. Okay. All right. Sketch the path of the bird between time 0 and time 2 seconds. Okay. All right. So we got to sketch the path between time 0 and time 2 seconds. Okay. All right, well, what was it at time 0? At time 0, it's going to be what? All right, now look. Okay, notice its x component. All right, at time 0, that goes to 0, right? So let's just look at it, okay? So x with respect to time at 0, alpha, gummit. All right, I hate it when I do that. All right, what is that? Oh, 2.4? Yeah, so we got 2.4 meters, that's a 4, per second, times 0 is 0, right? So where are we on our x-axis? For x, we're at what? We're right there at the origin, aren't we? Okay, but what about for y? Okay, well, we got y at time equals 0. Well, we got is equal to what? 3 meters minus, what was that, 1.2 meters per second squared times 0. So what are we left with? Y at time 0 is 3 meters, isn't it? So our graph should look something like this right here, shouldn't it? Boom, right there, right? So you would draw your arrow to that point right there. We're just approximating. We're saying 3 meters. All right? Now, what about at time 2 seconds? It did say do it for 2 seconds, didn't it? Yeah. Okay, all right. So at x is equal to time x at time 2 seconds. So we plug in, we got 2.4 meters per second times 2 seconds. And what do we get? 4.8, yeah. Duh, I didn't even have to calculate that. All right. And then at y at 2 seconds, so we got what? 1.2, no, whoa, we got 3 meters minus 1.2 meters per second squared times 2 seconds squared. And we should get a negative 1.8, right? Yeah? All right, so now let's draw it. Okay? All right, so here's your axis. Okay, right? Okay, so where would 3 meters be on the x-axis? Probably about what? Right there? And where would 1.8 be on the y? Negative 1.8. Let's say, let me come on out a little bit farther. Let's say 3 meters is right there. And let's say negative 1.8 is what? About right there? So draw your arrow. Does that look right? In other words, it's closer to the x than it is the y, right? Because x is greater than y. So that's what you do on that part. Does that make physical sense? Okay, then what does it say? Okay, calculate the velocity and acceleration vectors of the birds as a function of time. Okay, so we want to do velocity and we want to do acceleration. Okay, all right. It says calculate them. All right, now notice these are functions with respect to time. Both of them are displacement. So what do I need to do? That's right, first and second derivative. So the first derivative is what? For Vx, velocity in the x is what? It's just alpha, isn't it? Because remember, what was it? X with respect to time was what? Alpha t. So velocity in the x direction with respect to time is just going to be alpha, isn't it? And that's going to be equal to what? 2.4? Yeah. 2.4 meters per second. Okay. All right. And what is acceleration going to be? Zero. Yeah. Right? You say, how do you know that? All right. What? You just said it, Scott. What is the velocity right here? It's constant. How do I know that? There's no time. There's no t. Right? See, look at you. Look after we took the derivative. There's no t in our velocity function. You see what I'm saying? It's just alpha. That's how you know it's constant. So if velocity's constant, acceleration, y'all, has to be 0. Because there's no changing velocity. I mean, okay? Because how do we define acceleration? Rate of change in velocity. There's no change in velocity, there's no acceleration. Okay. All right. Now let's do for the y direction. Now we can go ahead if you want to. We can label it ij. We don't have to. We can. All right. Just put the in parentheses and put I in the caret cap. We can. All right. Now let's look at y. Y with respect to time was what? It was 3 meters per second? Yeah, 3 meters per second. Yeah, 3 meters per second minus bt squared. All right. Okay. So when we take the velocity, and this is in the y direction, the 3's gone, isn't it? So it's negative 2 beta, isn't it? Beta t. Very good. All right. So is velocity constant here? No, because there's a t. It's changing with time. All right? And so you just do what? So that's going to be equal to 2 times, was it 1.2? Yeah, 1.2 meters per second squared times, all right, well now we know, what is it going to be at time, let's see, now wait a minute, what did it ask again? Sketch, calculate the velocity and acceleration vectors as a birds as a function of time. Okay. At time 0, what is the velocity in the y direction going to be? 0 meters per second. Okay. At time 2 seconds, it's what? Well, yeah. It's going to be what? 4.8? Thank you, negative 4.8. All right? Right? And you say, how do you get meters per second out of that? That cancels right there. And it's meters per second is all that's left, right? Okay. Okay. All right. Does everybody see how we did this? This is at time equals 0, and this is the velocity in the y at time is equal to 2. Okay? Okay, everybody good? Makes sense. All right, what's C part? Calculate the magnitude and direction of the bird's velocity and acceleration at 2 seconds. Okay? All right. Oh, did I leave something off?
Yeah, I just wanted it as a function of time. So
Yes.
We didn't want a direct answer, right? So wouldn't it be like...
Yeah, oh, yes. You wouldn't actually have to plug the values in. Yes, you're right. Yes, I apologize. Yeah. So it'd just be what? It would be that right there, and it would be this right here, wouldn't it? Thank you. You're right. Because it says as a function of time. You're exactly right. All right. Then we go ahead and plug it in. Calculate the magnitude and direction of the bird's velocity at time 2 seconds. Okay, let's do the velocity first, and then we'll do the acceleration. All right, so what's the velocity? We already know what? Part C, the velocity is what? It's constant, isn't it? In the x direction, that's right. So it's 2.4 meters per second, period. Because the velocity in the x direction is constant. But in the y direction, we've already calculated what? It's 4.8, isn't it? The velocity in the y, negative 4.8 meters per second, okay? But now notice it says calculate the magnitude, okay? Magnitude. Those are my components. Those are my x and y components. That tells me how far in the x it's going and how far in the y. That's not what it's asking. It says it calculate the magnitude. So what do we got to do? All right, so we're going to do, now look, I can write it, and I have to be careful writing R because now we've done relative velocity. So if we just want to do this, magnitude, if you want to write it that way, because I have to be careful writing R because I don't want you to think, what I mean by that is resultant, but you know that, but I don't want to confuse you. So we'll do magnitude, and so we do what? Square root of the squares, don't we? So we do 2.4, and I'm going to leave the units off if that's okay, plus what, 4.8, and that's a negative, but you know the negative's going to go away. And what do you get? 5.37? Yeah, okay, that'd be good. I'd count that on a test. 5.37 meters per second. All right. Now, what about the acceleration? Okay. Did we go ahead and calculate the acceleration? No. All right, what did we determine on the acceleration in the x? It's 0 meters per second, right? All right, what is it in the y? All right. Okay, so we got to do what to this right here? We got to take the derivative again, and so the acceleration of the y is equal to what? 2 beta, isn't it? Negative 2 beta, thank you, which would be what? Negative 2 times, and you're right, Scott, 1.2 meters per second, and you get what? 2.4, and it's what? Negative meters per second squared, right? Why do I feel like I'm leaving something off? That's supposed to be squared right there, isn't it? Yeah. Thank you.
The vector notation would just be 2.4 270 degrees. Because it's just a
Yeah. Okay. So, but what's the magnitude of the, yes, what's the magnitude of the acceleration?
2.4.
Okay, yeah. We end up, if we go ahead and do the square root of the squares, right, what do we get? We got 0 meters per second squared plus what? 2.4 squared, and what do we get? 2.4, yeah. Yeah, absolutely.
Only y
That's right.
is negative on the y, which is 270.
Okay. All right, now, what does it ask for? Does it ask for direction?
Yes, it does.
It says calculate the magnitude direction of the bird's velocity and acceleration. Okay. What would its, let's see, what would its velocity direction be? Theta for velocity is going to be what? Negative 4.8, arctan, right? Arctan, negative 4.8, and yes, you better put that negative in there. And we get what? We get a negative 63.4, which winds up being,
296.6.
yeah. And how do we know that? All right, remember what I always said, y'all. I've said it 1,000 times. Draw your coordinates. All right, so where is negative 4.8? It's down here, isn't it? Positive 2.4. So it's going to be in the fourth quadrant, isn't it? Yeah, that's pretty close right there. Close enough. So am I going to do what? I'm going to take 360 minus 63.4. Actually, we're adding them together, but it comes out to be, what'd you say, 290 what?
296.6.
Okay, and that's the answer I want to see on the exam. All right, now what about the acceleration? Well, we do arctan of the acceleration, and that's what? Undefined, yeah. Yeah, absolutely. So that, how do you write undefined?
Well, the arctan of undefined is pi over 2, and then you set it based on positive and negative.
Yes.
So,
Okay. So we know it's going to be undefined, and so we have to go back to our,
the first tangent answer is undefined.
yeah,
The
yeah.
argument is undefined.
Argument's undefined, yeah. And so we wind up with what? 270 degrees? Yeah. Because look, there's no x. And you say, how do you know? And really I didn't even need to do arctan. Because look, there's no x. It's 0. So it's just 2.4. Straight down is 270. You know that. All right, very good. Okay? Now, could we have one like that on the exam? Maybe. You're going to have one possibly very similar. Some of these are similar. Okay? So, you know, you might want to kind of put a star by that one, kind of look over that one. Okay? Okay? All right. And we did number 3 the other day, didn't we? You might want to put a star by that one. Okay. Now, again, not the whole thing. We're not going to do the whole thing. Okay? Because that's too many steps. I mean, come on, y'all. If I did that, we'd be here, what, 20 minutes on one problem? Yeah, we don't want to do that. Okay. All right. Okay? Yes? All right, if you draw it, let's look at it. Let's just look at our points. X, acceleration in the X is 0, right there at the origin. Acceleration in the Y is negative 2.4, which, well, let's just say it's going to be right there. Yeah, you see what I'm saying? Straight down, 270. Okay? All right, very good. All right, wonderful. Okay? All right, do y'all want me to do the firehouse problem anyway? Okay, let's look at it. Or it is firehouse, right? Fireman problem, whatever you want to call it. Yeah. Number 20. Let's go ahead and look at it. We might go back and look at number 1 too. I don't know. Y'all seem to be good with it. I love problems like this. Okay. That other problem's great too. It's a good problem. But I mean, this is something. I mean, when you start talking about X and Y and all that, it's kind of hard to get it in your head. But when you can see somebody shooting a fire hose at a building, I mean, that's something you can physically see happen. Okay. All right, so we got a high-pressure hose to shoot a stream of water at a burning building. Okay, so let's draw our building over here. All right, so we got little Johnny up here screaming for help. All right, okay. And so we got flames coming out of it here. And, okay, oh my God. All right, that's really not funny. But anyway, okay. But we're going to get him. We're going to take care of him, all right? The water has a speed of 25 meters per second, all right? So we got to, let's draw the ground. Okay, we're not floating in space. And so we got a fireman over here, okay? And he's holding a hose. Okay, and there's his hose, okay? And there's the fire hydrant, all right? And the angle is what? 25 degrees, is that right? No, it's coming out, I'm sorry. So the initial velocity out of the hose is 25 meters per second. I actually need to steepen that hose a little bit. Okay? Okay, so let's, come on now. All right, so let's angle it up like that. And so the water's going to go boom, like that, isn't it? Okay? Now notice that's initial velocity. Okay? As it leaves the hose and exhibits projectile motion, the fireman adjusts the angle of the hose until elevation of the hose until the water takes 3 seconds to get there. So from here to here, the time is 3 seconds. Okay? Times 3 seconds, all right? And the building is what? 45 meters away. So from here to here is 45 meters. What will we label that? Delta X or X final? You could say it one of two ways. You can say the change in X is 45 meters because look, this over here, X initial is 0. X final is 45 meters. Okay? So however you want to label it, okay? And unless it tells you initial displacement is this, typically it'll say starts at rest. If it doesn't say start at rest and it doesn't tell you initial X, then you just assume it to be 0. Okay? All right. We good with that? All right. Okay. Ignore air resistance. Assume that the end of the hose is at ground level. So in other words, I didn't really draw it completely right. The hose is actually down here, isn't it? So the hose is right there. Okay? All right? Okay. All right? Find alpha. Okay, so we got to find alpha, don't we? Can we find alpha? It should be pretty easy, shouldn't it? All right, because we know what? We know the time. We know change in X. We know initial velocity. Okay. We don't know final velocity yet. All right. All right. What are we going to have to do to our velocity right here? That's just velocity. So what's the velocity in the X direction? Go back to your formulas, your projectile formulas. Yep, so it's 25 meters per second. Cosine of what? The angle, isn't it? Right? So we don't know what it is yet, right? Same thing for the Y. And that's V in the X and V in the Y, except it's going to be sine, isn't it? Sine theta, all right? Okay, well that doesn't help us as far as that goes yet. All right, can we find the distance from here to here? Well, we're given distance, aren't we? All right, if I was not given the distance, but I was given the time and I was given the angle, can I find it? The initial cosine of theta times what? Times the time, right? This is one of your equations I gave you the other day. It's on page 79, I think. I think it's on 79. Let me double check. Excuse me, 76. 76. Okay? So we can solve for theta, can't we? All right, now let's identify some things here. Something else I left off. What do we know about acceleration? I've completely left that off. Acceleration in the x direction is going to be what? 0? Yeah? What about acceleration in the y direction? Negative 9.8? Okay. So now, can we find the theta? So what is theta? Can we find it using that equation? Is it going to be this right here? Taking this equation right here. It's going to be what? Arc cosine of what? Is it velocity over time or displacement over time? It's what? It's this right here. Arc cosine. Now look, divide both sides by velocity. All right? And by what? The time, right? Is that what the equation's going to look like? Take this equation right here and solve for theta. So we got 45 meters over what? No. Velocity. Initial velocity. Okay. So it's what? 25, and that's meters per second times 3 seconds. And we wind up with what? After we take arc tan, 53.1 degrees. Does that make sense? Okay, now let me explain something here. Well, why didn't you use y? I don't need to use y. Now look, y'all. The time it takes to go from here to here, okay, is going to be the same. We're not looking for how long did it take to reach its highest point. Okay? Highest point is y. Now, could we find that? Yeah. Yeah, we could with a different equation. That's not what it asks. So it's asking how long did it take from here to here. Okay? And, of course, we had to find theta. It gave us the time, though. Here we had to find theta. What if I gave you theta and asked you to find the time? What if I gave you the angle and said, okay, here's the distance. How long will it take to get there? Okay? You just solve for t. Yeah. Okay? Now, folks, I'm telling you, it's so important to label everything first. See, I almost forgot about my acceleration. I almost left those off. So label everything that we know that's given to us, okay? Any questions about that? So that's theta. All right, what's the second part? Part B. Now, again, I'm not going to give you 3 or 4 parts. I'll give you at least 2 on this one if I gave it to you. Find the speed and acceleration of water at the highest point in its trajectory. At the highest point. Okay? All right. That's a good one. All right. So what is acceleration in the x direction? We've already determined that. All right. When it comes out of the hose in the x direction, is there any acceleration once it comes out of the hose in the x direction?
The initial acceleration.
No.
Acceleration doesn't
Oh,
push it.
yes.
In the x direction. In the x direction. Because see, what's pushing it? Once it comes out of the hose, it's out of the hose. It's on its own. So there's nothing behind the water in the x direction giving it more acceleration, pushing it. Okay, in the x direction. So it's 0 meters per second, isn't it? Squared. What about in the y direction? Always. That's that conceptual stuff. Remember I did the demos? Remember we're shooting the monkey? Same principle here. Just because it's a different setup, that doesn't change gravity. It doesn't change anything. All right. 9.8. Okay? Okay. All right. Let me make sure I didn't leave it. Find the speed and acceleration of the water at the highest point in its trajectory. Okay? Okay. All right. So that is what? Well, we know what what is the acceleration in the, excuse me, now that's acceleration. What is the velocity going to be in the x direction? How do we find that? Huh? Some of y'all are saying it. But we're going to do what? Cosine of 53.1. And what do we get? 15 meters per second. Now that's going to be all the way through from the time it goes, all right? All the way through in the x direction. Same speed. Okay? Same speed. All right? Now notice it said, boy, here we got to watch. At its highest point. So right here. It's talking about right there. What is it going to be in the y direction at its highest point? Y direction. All right, if I draw my axis here, my x and y axis, at this point, is it going up anymore? Is y changing at its highest point? Y is not changing at its highest point, is it? Uh-oh. So that means the change in y is what? And when I divide that by time, what do I get? 0. So the velocity in the y direction is what? At its highest point now. Okay? Does everybody agree with that? That's again conceptual. Thinking about, you got to think about, oh yeah, I'm going up, and if I'm going up to my highest point, I'm not changing direction anymore. I'm at my highest point. That means my velocity has to go to 0 for just a brief moment in the y direction. Okay, just a split second. Okay, all right. All right. What about 20C? 20C. All right. Oh, me. The horizontal range from the base of the building to the point where the rock strikes. Oh, I'm reading the wrong dang problem. The water. I'm reading the next problem. All right. Find the speed and acceleration of the water at the highest point strike. How high above the ground does the water strike the building? So that's what? That's y final, isn't it? Y final. All right. Did we have this equation right here? Okay. All right, I'm gonna go ahead and do this. I'm gonna say plus. Okay. No, I'm not. I'm gonna do this. I'm gonna keep it. I'm gonna keep it synchronized. Minus GT. 1/2 GT squared. Right. Okay. All right. Now, what was y initial? Did we define that a minute ago? Y initial is what? 0 meters, right? Starting at the ground. So y initial is 0 meters, right? So that means this term right here is what? Gone, isn't it? Okay? We know our time interval. So let's just plug it in. Y final is equal to, all right, if you want to go ahead and plug it in, 0 meters plus, what was the initial velocity? 25 meters per second, sine of 53.1 degrees times 3 seconds minus, now watch, 9.8. I don't say minus. The minus is already in there. Times 3 seconds squared. And you should get, do what now? 1/2. Ah, dang it. Yeah, thank you. 1/2, sorry. Hey, by the way, if you want to, On that equation, you can just make it 4.9 and leave the 1/2 off. I mean, you probably already figured that out, but you don't have to show it. If you take half of gravity and go ahead and plug it in, you're good, okay? All right. I meant to tell you that, but I figured you saw that. I mean, if you didn't, now you do. Okay. So Y final is what, 15.9 meters? All right, let's draw that. What's that going to look like? All right, so we got ground level. We got our hose is at ground level, and so it's doing something like that right there, isn't it? And so this is 15.9 meters. Okay? All right. Okay. Now what's the next part? And, oh yeah, we didn't finish it. And how fast is it moving just before it hits the building? How fast is it moving? Well, we know initial velocity, don't we? Initial velocity, or velocity in the Y is what? 25 meters per second? And this is initial now, times what? Sine of 53.1, right? So what is the final velocity? Y, velocity final in the Y direction. Okay? Well, it's not zero. It's not zero. I want to know right there, I mean, just as it gets to the building, what is it? Right there. Well, do we have this equation right here? GT, yeah. Is that right? Is that right? Y'all keep me on my toes now.
You sure that's right for the height?
Yeah, 15.9, yeah.
That's not what I'm getting. I'm putting it the same.
Okay, well, let me double check it then. All right, so we got 4.9. Let me just do it this way. So we got 25 sine of what? 53.1?
Oh, never mind. I see where
Catch it? Okay, good. I mean, that's fine. Just double check me because I might write something down wrong sometimes. That's good. All right. All right, V final is equal to. All right, so we got what? 25 meters per second. Sine of 53.1, right? Minus 9.8 meters per second squared times what? 3 seconds. And you should get an answer of negative 9.4. Negative 9.4 meters per second. Huh, so what was it doing? The stream of water was already doing what? It was already going down, wasn't it? I should have made that the arc a little bit higher here. That way you can see it's going down. Right? Negative 9.4. Okay. Now let me ask you this. What if, now the problem did not ask you this. I don't think it did it? Oh, yes. Ooh, yes. It said how fast. It didn't say what was the Y velocity. It didn't say what was the X velocity. What is the X velocity? That's in the Y, right? What was it in the X? We've already calculated it. 15 meters per second. So V X final is 15 meters per second. It wants to know what is how fast or the speed, and what are those quantities? Vector or scalar?
Scalar.
Scalar. So what do we got to do now? How do we find the magnitude?
Take squared.
Square the squares. So velocity magnitude is equal to square root of the squares. Very good. And I'm going to leave the units off. And listen, when you're doing this on the test, boy, some people might shoot me for saying this. For the sake of brevity, I mean, if you want to leave your units off while you're doing like the square root of the squares thing, just make sure you put them on at the end. I mean, you need to start out with everything, but as you're calculating, just for the sake of brevity, you can leave them off till you get to the end. Just make sure you know where you are. Now, if you don't want to, fine, but I know it takes more time to write. and that's negative. Of course, the negative's going to go away. We know that. And that's all on the radical now. Can you see my radical? And so what do we get? 17.7? Okay. Sure.
When solving for the VY final,
Uh-huh.
do not use the VY initial.
Yeah.
Okay, because when I solve for the VY initial, the 25 sine 3.1, I got 19.99.
Yes, you could do it that way. Yeah, you could go ahead and use that. Did I not put it here? I put 25 meters per second sine of 53.1. So yeah, so when you take the sine of 25, isn't that what you got? 25 sine of 53.1.
I didn't use 20. I was solving for the VY final, so I used the VY initial, which is almost 20.
Yeah.
So I got negative 13.20.
So you use negative 20 right here? I mean, I'm sorry, you use 19 or 20? Okay. All right. It should still work. So you went ahead and did it and put it in. I see what you're saying. So what'd you get, 19 point what?
Well, the VY initial is 19.99.
Okay, we'll just say 20.
Okay, and then the VY final,
Okay.
what I got was negative 13.4.
Okay. Times 3. Negative 9.4. Yeah. All right. That's fine. I think maybe you might have something right here because it's not. Were you squaring this number? Were you? Okay. So it'll be, let's just say 20. 20 minus, and then 9.8 times 3. You should get negative 9.4.
Am I supposed to square 3?
No. No.
Okay.
No.
Yeah, I'm still getting 13.
Okay. That's strange. Okay. So let's just say 20. All right, so watch. So we got 20 minus 9.8 times 3. Okay. It's just, you might be punching the button wrong or something. Okay. It happens. Okay.
I got the same thing.
You're getting the same thing? Well, I don't know how the heck you're getting that.
I think what he's doing is he's taking the velocity initial, the VY
Yeah.
equals 25 sine, and he's actually plugging it in and getting 19. And then from there, then he's plugging it into velocity F final, because velocity initial sine stayed up.
Oh.
Plugging it in.
Okay.
Then he's going and, plugging the entire thing in, then he's getting his answer, which is 13.
Okay.
Negative.
Okay. All right. So in other words, you're telling me he's plugging it in here and then going back?
See, yeah, you put in a 25. He
Uh-huh.
actually did the velocity initial up there, and then got a 20 or a 19.
Yeah, it comes out to be 20 right at it.
Right. So
Okay.
That's how he's getting the 13. You did 25 and got negative 9.4.
Okay, but I'm saying sine of 53.1 and 25 sine of 53.1 is 20, right?
Essentially.
Yeah. Okay. Yeah. That's what it is. Sine of 25 sine of 53.1 is 20. Right at it. Okay?
No. What I'm doing is instead of using the VI, I'm using VYI in the formula.
Okay. Yeah. I still don't see how you're getting.
I'm using 20 sine 53.1.
No, that's not what you're supposed to do. Yeah.
Yeah.
Because remember, when we're looking for V final in the y direction, or excuse me, yeah, when we're looking for V final in the y direction, you have to use your initial velocity. You can do it one of two ways. You can say the initial velocity in the y, okay, is going to be what? Well, it's 25 sine of 53.1. You don't go ahead and do it and then stick it in. I see what you're doing now, yeah. Because this is in the y direction. V final is V final. Okay? Period. All right? We're talking about y direction only. Okay? To find y. So you don't have to take the sine and then stick it in. Yeah, I see what you're saying now, yeah. You're doing it You're taking the sine twice is what you're doing.
Yeah.
You see what I'm saying? And you're not supposed to do that. You don't do that. You're taking the sine twice. Say, look, if you, all right, V final is equal to V. All right, let's just look at it if it's one-dimensional motion. Yeah, let's just say this right here. All right. Okay, but when we go at projectile, okay, then we've got to take the initial and say this right here. The initial sine theta, okay? All right.
Does that say V initial plus AT?
Yes, plus AT.
I was reading the formula, the V is equal to V sine theta minus 3.
Yeah. VI is VI.
I thought you were wanting us to create it into VY final and using the VY initial instead of VI.
Yeah, I see what you're saying, yeah. Yeah, it's VI, period, yeah. All right, let's, while we're talking about that, because this is something we need to iron out, okay. If you go back, let's see, let's look at page, what was that page, 76? Yeah, notice it says V naught, equation 3.22. V naught is V initial, period. Okay, so yeah. Yeah, you don't, because you were taking the sine twice. Yeah, okay. Okay, all right. All right? Yeah, anytime you see V naught or V initial, that is not taking into consideration the x and y directions. That's just saying initial velocity. You have to find for what it is in the x and y by doing sine and cosine. Now, you could have, like I said, just gone ahead and taken it and put it in here and then done it. It's the same thing. Okay? All right, negative 9.4. And then we get a what? Resultant of 17.7. That's the magnitude. So let's not forget that when the question says speed, all right, here again, y'all, terminology just seems to choke us sometimes. What does it mean when it's asking for speed? Well, if you've got an x and y direction, you've got to do what? You've got to take the square root of the squares. You've got components. And so if it says what are the components of the velocity, then you would give me what? The velocity in the what? X, and the velocity in the y. Or ij. You can label it ij. Either way, it's the same difference, right? Okay? So components, x and y. Speed or fast, square root of the squares. So again, that's terminology. What is it asking for? Well, it said fast. Well, that's speed, and that's magnitude, and that's square root of the squares. Okay? And y'all, I try my best on these tests. And I know some of these questions, y'all, I've read them and read them and read them. Some of them, they are a little bit, they're not really, the way they use the word magnitude sometimes can throw you. Okay? But on my test, I try to keep it, make it very plain what I'm asking for. Okay? All right, good.